All right, today we're going to pull back the curtain on a concept that is quite literally powering the modern world, even if you've never heard its name. We're talking about pulse width modulation, or as you'll usually hear it, PWM. So let's jump right in. So think about it for a sec. If you want to dim an LED, or maybe make a fan spin just a little bit slower, how do you actually pull that off? Now, the obvious answer might be, well, just give it less power, right? But what if there's a smarter, way more efficient, and totally digital way to get it done?
You see, you could go the old school analog route and just lower the voltage, but modern electronics, they love digital. So instead of giving a device less power, what if we give it full power, but we just flick the switch on and off like thousands of times a second? That simple, crazy fast switch, that is the big idea behind pulse width modulation.
So what is this PWM thing, really? Well, believe it or not, the name itself tells you pretty much everything you need to know. Okay, at its heart, PWM is a super clever trick. It's a way for us to get what looks like an analog result, a light that dims smoothly, by using a purely digital signal. And digital can only be two things, all the way on or all the way off. The magic, the real secret sauce, is in controlling how long the signal stays on versus how long it stays off. Just imagine you're standing at a light switch, but instead of a dimmer dial, all you have is the switch. If you flick it on for just a tiny blip and then off for a while, the light's going to look dim, right? But if you leave it on for longer and flick it off for just a moment, it's going to look bright. That's PWM in a nutshell. Now, to control this whole effect with any kind of precision, we need a way to talk about that on-to-off ratio. And that brings us to the most important term of all here, the duty cycle. This is the key to everything. The duty cycle is really just a percentage. That's it. It tells us for any little slice of time what percentage of that time the signal is on. So a low duty cycle means it's mostly off. A high duty cycle means it's mostly on. It's the one number that lets us control the whole show.
And check out this table. It lays out the relationship perfectly. You can see how the duty cycle percentage directly changes how bright that LED appears. 10%, super short on time, so it's dim. 90%, it's on almost the entire time, so it's super bright. Let's look at a few of these a little closer. So at a 10% duty cycle, the power is on for just a tenth of the time, and it's off for the other 9/10. To our eyes, this super fast flicker is way too quick to see. Our brain just averages it all out, and we perceive a steady but dim light. Now let's bump that up to a 50% duty cycle. Here, everything is perfectly balanced. The power is on for half the time and off for half the time. So what you get is exactly half of the total possible power, which gives you a nice, medium brightness. And at 100%, well, that's easy. There's no off time at all. The signal is just constantly on, full blast. This is exactly the same as just hooking the LEDs straight up to the power source. It's getting all the juice, so it's at maximum brightness. Okay, so theory is one thing, but how does this actually look in the real world? Let's talk about how this all comes together in a simple, hands-on circuit. So in a classic little project, you might have a microcontroller, something like an Arduino, and it's the thing creating these super fast pulses. Then you hook up a knob, a potentiometer. But here's the cool part. When you turn that knob, you're not actually dimming the light directly. You're just telling the Arduino, hey, change the duty cycle, make the on pulses longer or make them shorter. And our eyes see that change as the LED smoothly getting brighter and dimmer. And this right here is the absolute key. The switching is happening so incredibly fast that you literally can't see the individual flashes. Your brain just mushes it all together and averages it out. So you don't see a flickering light, you see a solid light that's just dimmer. It's an amazing optical illusion, all driven by digital precision. So let's be crystal clear. The LED is always getting the same voltage when it's on. It's never getting half voltage. It's getting full voltage just for a shorter amount of time. And this is way, way more efficient than older analog methods that would just burn off extra energy as wasted heat. Okay, so dimming an LED is a cool party trick, but why is PWM so incredibly important in modern electronics? Well, its uses go way, way beyond just making lights look pretty. I mean, that same exact principle we used for a tiny LED, it can be scaled up to control the speed of a massive industrial motor with incredible precision. It's also the secret sauce inside the switch mode power supplies that run your computer, your phone charger, pretty much everything. And this right here is its superpower. You can use a tiny, low-power signal from a little computer chip to perfectly manage a huge amount of power flowing to something massive, like a motor. It's like having a tiny brain that can precisely control a giant muscle, which makes it one of the most powerful tools an engineer has.
So the next time you see a light dimming smoothly or you hear a fan in your computer change speeds, just remember the invisible magic that's making it happen. It's probably not a smooth analog flow of power. It's a lightning-fast series of digital pulses, creating the world that we see and feel. So I'll leave you with this. What do you think is using PWM around you right now?